Hello, good evening, everyone. Welcome to the event for yourself, and also thanks for coming to this talk. I actually used to come to this event myself with my family almost every week on Wednesdays, ever since we arrived here at Cambridge, which was a couple of months ago. But then, since my wife and I work together with my young children from home to here, which is just 10 or 15 minutes, foot distance. But since we work together with them, no matter how early we leave home, we normally find ourselves arriving late or just a couple of minutes before the beginning of the lecture. And as a result, we normally find only the least popular seats unoccupied or very first, which are normally seats that are too close to the screen. But since today I'm the speaker, I couldn't be late, so I left home alone and earlier than usual, but only to find a spot that is even closer to the screen. And there's not even a seat here, so I guess I wouldn't complain in the future even if I find only the seats that are too close to the screen. So sorry for much ado. So my name is Seungwan. I'm definitely an astronomer or astrophysicist, and my office is actually in the building right next to this one, so which is called the Kavli Building or KICC. So you will pass by that building when you are heading for our stargazing event after this lecture. And what I'm going to talk about today is protoclusters or clusters. So, and I assume that a majority of you in this room probably would never heard of what protoclusters are, or maybe even what clusters are. But as just its name suggests, literally from the name, clusters are actually regions with a relatively small region in terms of volume, but with a lot of galaxies clustered in. So it's like big cities. I mean, for human beings on the Earth, like London, for instance. But then protocluster obviously has a proto in front of the word cluster. So protoclusters are some kind of progenitors of the clusters. So protoclusters are things that had pre-existed before the formation of clusters that eventually resulted in a cluster at a later time. So it can be considered as ancient cities or ancient metropolis, or even medieval London or something like that. So before I lose the attention from the youngest ones in this room, I'm gonna play this little video clip. So this is not the real universe, caution. This is what we call simulation. So this is simulated universe that we hopefully closely mimic the real universe. And this video clip starts when the universe was only couple 100 million years old. So I just said only because the current age of the universe is estimated to be 13.7 billion year-ish old. So if we scale that down to humans' lifespan of let's say 80 years old, then this video clip starts when the universe was like 2-year-old or 3-year-old baby. So that's how early this video clip begins. And what will be shown is specifically the gas distribution, so distribution of the gas and mainly hydrogen. But normally those gases associated with the old other types of matter as well, including even dark matter. So you can take this roughly as a matter distribution in the universe as well. So the bright regions are actually regions with a lot of gas and matter, and the pinkish empty regions, pinkish regions are sort of empty regions, or with the regions with a lot less matter density and gas density. And in this video clip, the time interval between each frame is actually 40 million years. So if I go back to that analogy, human lifespan analogy, that corresponds to about 3 months, so about a season. So that's how. So literally. Time literally flies in this video clip, so that's how fast this is gonna go. So yes, so no more ado, and I am gonna play this video clip. So it begins from this thread-like structure, filamentary-looking structure, but then they shrink and getting close to each other, and also getting bigger because of the gravitational attraction between them, and then. How do I, oops, it doesn't work. Sorry, it's going too fast. And then, so we are just passing the rest to 2. So that's again, going back to humans' lifespan, that corresponds to about, 20 years old human beings. So the universe just began to sort of university. And then, so we began from the filamentary structure, but now we are just also beginning to see that, these small, very little small bright blobs, right? So they are in sort of spherical, and you can consider that as, since they are gas distribution, as I said, so those are regions with the very high gas density. So you can consider each of these as an individual galaxy. And we also begin to see that, so we began from the filamentary structure, but now that feature, that thread-like structure is more or less diminished, and then we instead begin to see a couple of these very bright. Maybe this laser pointer works better. Well, I will try this one. Yeah, so there are a couple of these bright, spherical, regions, and they are actually the central regions or cores of protoclusters, and at the same time, they are the seeds that evolve eventually into a cluster at a later time. Yeah, so the filamentary structure, continuously getting diminished, and instead, we begin to see more and bigger, spherical, bright regions. And then now we are passing just a ref to 1, so that's about when the universe was half the age of current universe. So like, for human, it's like 30 years old or 40 years old. So, those individuals are like humans are, maybe not these days, but humans used to be, these individual regions are getting mature and getting bigger, and they are sort of getting close to each other to sort of get married. And then there are, also a couple of other still bright but relatively, less bright regions that are also approaching, sort of like keys to children to, harass and bother their parents at a later time. Sorry to say that. So yeah, so those couple of spherical regions are getting bigger and bigger, creating more and more. And like I said, even these two brightest ones are getting, sort of merging into each other to form a single cluster, and some other, keys or some other less bright ones are also getting close. But there are still a lot of also individual small galaxies continuously falling. Oops. So this is the. How do I go back to the? Maybe I can't. Okay, so that last, sorry, that worked on my laptop, but yeah. So the last thing that you remember that you saw that so a lot of small galaxies continuous falling, and then a couple of brightest spots at the center. That's the end of the video clip. That's the sort of present day, of course, of not of the real universe, but of the simulation. But that's what we call cluster eventually, and everything that preceded that resulted in that formation of that cluster is what we call protoclusters. So what we do know for sure now is that we are not alone. I mean, maybe not in terms of intelligent creature, but at least we are not alone in terms of galaxies and objects in the universe. So other than our own Milky Way galaxy, well, this is very rough ballpark number, but we, more or less, give or take like 1 trillion-ish galaxies are there in our universe. So for Keith's benefit, so 1 trillion is if you put 1, and if you put 1 0 next to it, then that's 10, right? Then if you put 1 2 zeros, that's 100, right? Then trillion is you put 1 and then follow that with the 12 zeros. So that's trillion. That's how big that number is, and that's how many galaxies are in our universe. So this image is actually very small, very, very small portion of the entire universe, what is shown here. So this is sort of our neighborhood. But even in this small portion of the universe, we already see a lot of galaxies. So each little black dot, each of these little black dots is individual galaxy. And within this neighborhood, where are we? We are here in the Milky Way. So not even the entire yellow circle, but one of those little, actually they are clusters, so I cannot pinpoint which one that is, but one of those black dot that little thin red arrow is pointing to, that's where we are. That's our Milky Way. But then you also notice that, so I said that each little black dot is a galaxy, but then those points are actually indicating only the position of a galaxy. But you also notice that there are a hairy line or straight line that is connected to each of those little black dots. And actually that lines are showing the velocity field of galaxies. So that shows which direction galaxies are moving toward. So for instance, if you focus on the Milky Way and galaxies near the Milky Way, then actually the direction of those straight lines are actually not random, but actually they are quite coherent. They are heading toward one direction, which is this direction. So if you follow that direction, then you end up here. So this is today's topic. So this is one example cluster. So like I said, cluster is the region with a lot of galaxies clustered in relatively small volume, and this is what that is. So there are a lot of black dots, galaxies that even we cannot distinguish between those dots at the central region. And this particular cluster has a name, which is Virgo cluster, because the cluster is actually located on the sky in the direction to the Virgo constellation. And Virgo cluster happens to be also the nearest cluster from us, so from Milky Way. So we technically, so our Milky Way currently does not technically belong to Virgo cluster. We are just located over the edge of the Virgo cluster, but we are heading toward that direction. So Milky Way, after a long time, like cosmological times later, Milky Way will be eventually joining the Virgo cluster to be one of its members. But of course, none of us in this room will be able to see that happen. So this is a very simplified image where each galaxy is represented by a little black dot. But the real image of Virgo cluster is like this. So this is a real image, real observation. But this is a 2D projected sky. So everything along the line of sight is being seen. So there are actually a lot of background galaxies that are too far away and that do not belong to the Virgo cluster. And most of those galaxies, background galaxies appear, too small, like tiny dot and relatively fainter. But all the other galaxies, like, bigger ones and bright ones, brightest ones that your eyes can see, actually, they are actually real member galaxies that belong to the Virgo cluster. So I think there are, I don't know, I didn't count, but maybe there are 30 or 40 such galaxies that belong to the Virgo cluster, even in this small image. And so this shows how big a typical cluster is. So Virgo cluster is sort of, one of typical clusters. So this shows how big a typical cluster is and how many galaxies a typical cluster also has. So that's sort of today's topic, cluster. But then if we even go further beyond today's topic, then actually you also notice that, actually most of these straight lines that I mentioned earlier are not heading toward the Virgo cluster, but actually heading toward some other point in the space, right? Which is this area, right? So this is what we call great attractor. So it turned out that, well, there are some ambiguities when it comes to, whenever we find the largest scale structure, whether we call it, supercluster or cluster or protocluster, largest scale structure, there are different names, but it based on the fact that, most of these galaxies are actually heading toward great attractor rather than to Virgo cluster, indicates that the great attractor most likely has even more mass and even more matter and even more galaxies than the Virgo cluster does. But this one is not the end of the story. So actually, this is an even bigger map of where we are. So again, these hairy lines are, which directions galaxies are moving to. And again, our Milky Way is located here. And like I said, Milky Way is heading toward the Virgo cluster, so sort of connected. And then Virgo cluster and many other galaxies are heading further toward the great attractor. But great attractor is not the end, so it's not a root, but one of the branch, or even though it's the main branch. So even greater attractor is one of the main branches connected to the even bigger structure that looks like a ginseng, which we call Laniakea supercluster. I mean, there are, again, some ambiguities in its name, like, some people call it Laniakea supercluster, some people call it slightly differently, but at least it is quite, evident that this structure is even bigger than cluster like Virgo cluster. So this is our full neighborhood. So, our full address would be like Cambridge, Cambridgeshire, UK, Earth, Milky Way, Virgo cluster, great attractor, Laniakea, and the universe. Of course, most of these clusters or large scale structures do not have yet their postal code. And so those images have been mainly based on the real universe, so observations. And here I'm showing again clusters, but these are simulated clusters, so images of simulated clusters. And I sort of randomly picked up 2 examples. But even between these 2 examples, you can see there are a lot of similarities, but at the same time, there are some differences between the 2, right? For instance, so what is shown here is the distribution of stars, stellar components. So each little the bright blob is actually individual galaxy. So you can see that the one on the left actually has quite uniformly distributed, isotropically, like spherical distribution of galaxies. I mean, there is no particular direction that there are more galaxies or a lot more galaxies than the other directions. But on the other end, the one on the left, this example, has more like, elongated, a little bit more elongated distribution of galaxies and light in a vertical direction. And that's because this cluster is located within the filamentary structure or thread-like structure that we saw in the earlier, video clip, that the matter is being accreted, located along that filament and accreted along that filamentary structure to this cluster. So that's why in a vertical direction. So that's why this cluster has such morphology or distribution of galaxies. And here are just a dozen more examples of simulated clusters. So again, one common thing between all these clusters is that they do have a lot of galaxies surrounding them. But then the difference is, they are not exactly the same in size and morphology, I mean shape, etc. So why are they important? I mean, why are protoclusters or clusters are important? I mean, I said clusters eventually end up in a relatively small volume, but then they do also have a lot of mass in it, right? And the thing is, when the universe began, the matter distribution was quite uniform, and they began from a very low, uniformly distributed matter. So combining the fact that they began from very low density, uniform density, and then they ended up in a very highly concentrated small volume means that they actually accreted the mass from the very large fraction of volume of the universe, so that they collapsed all that matter to form very single small one eventually. So in that sense, protoclusters have affected and have used a lot of volume of the universe. So when they are combined, the protoclusters actually take up to 6% of the total volume, cosmic volume. So that's only 6%, but it's 6% of the entire universe volume. So that's huge. And because they take up such large volume fraction, also stars that have formed in the universe, or large fraction of stars that formed earlier in the universe, actually have formed within protoclusters regions. So we suspect that 22 up to 50%, so up to half the star formation that happened in the past in the universe actually have formed within the protocluster regions. And not only the volume, also the rate that the stars have been forming in protoclusters are actually about 10 times higher than that in the rest of the universe. However, as always, great things always come with the great challenges. So there are several critical challenges when it comes to studying protoclusters. And first of all, we do not have enough sample size. So sample size is very small. So far, we've confirmed only a couple of dozens of protoclusters from the observation, and that's definitely not an enough number to carry out statistically robust analysis to draw firm conclusions about the representative or the average properties of the whole population. And then another thing is protoclusters, they are invisible in our most familiar wavelengths, which is optical wavelengths or visible wavelengths that the human eyes can see. And that's because, galaxies early in the universe, they do have a lot of dust surrounding them, so that no matter how much star they have formed, the starlight from those stars cannot just get out of those galaxies, but they first observed by the dust, the surrounding dust. And then that dust reprocesses and re-emits the light, but not in the visible wavelengths, but in the other wavelengths that human eyes cannot see. And not only human eyes cannot see it, but that light actually doesn't even reach the ground of the Earth, because the Earth's atmosphere absorbs, most of those longer wavelengths lights. So that means, we have to send a telescope to the space to be able to observe and trace the protoclusters. And then maybe the most critical challenge is that, so for protoclusters, even though we are observing them, we are seeing their light right now, but that light had left them long time ago in the past. So we are basically, right now, we are seeing, but we are actually seeing their past. And there's no way that we can see their presence, since, their light, the light from them in the present hasn't arrived yet on us. But then for the clusters, it's the other way around. I mean, clusters are relatively nearby, so we are seeing their present, but we cannot see their past, since the light from those clusters in the past have actually passed us, long time ago, and we cannot back those light. We cannot get those light back to see their past. So for one thing, for protoclusters, we only see their past, but not the present. And then for the other thing, cluster, we only see their present, but not past. So it's logically impossible to link between clusters and protoclusters, or their present and past. So because of this issue, we heavily rely on what we call simulations. So simulated universe to study protoclusters. So here goes another just video clip that is very similar to the one that I showed earlier. So this also begins when the universe was really young, and it's going to be showing gas distribution, but you can approximate that as a matter distribution. But this is a more zoomed in version of the more zoomed in simulation, so you can see more detailed features if your eyes are good enough. So there is so at the bottom part of this screen, there is a region that a lot of gases are creating toward, because that's possibly the gravitational center. So there is a lot of matter already there, and then you just begin to see that there is a sort of fountain. Right? Can I go back here? Maybe it begins from the beginning. So there is a So when we pass around rest of 3, there is going to be something different that is going on if you focus on the bottom part of the screen, right? Yeah, you just begin to see sort of a fountain, right? And that's because that's because the supermassive black hole at the center of that galaxy that just began to work. So by ejecting a lot of energy outward and also pushing gas outward back to where it came from, but then continuously there is still continuous inflow as well. So there is an inflow and outflow with the balance yet to be reached. Yes, still there is a fountain and then also inflow. So there is there are a lot of things going on. And then there is another region here that supermassive black hole just began to work, pushing gas outward, right? And still a lot of individual small galaxies just flying by, or heading toward somewhere that is gravitationally attracting them. And then so far it's been showing mostly gas distribution, but from here on, it shifts to showing matter distributions. So actually stellar distribution, so you can consider these literally as galaxies from here on. So there are two brightest regions that are getting close to each other because of the gravitational attraction, but also there are a lot of small galaxies also associated with each of them that are still keep falling. And even these two ones will merge, but not at once because they do not have a head-on collision. So they pass by a couple of times until they finally merge to form a single cluster. And this is sort of present day. So this is the end of this video clip. So this is what we call cluster again, a lot of galaxies and couple of one or a couple of very bright central parts. Okay, so these are just snapshots from that video clip. So I'm gonna skip that. And given time, maybe I skip that, but there, so I just said I heavily, we heavily rely on simulations to study protoclusters, but there is no guarantee that those simulations actually match the real universe. And actually indeed find that, there are a lot of discrepancies between the simulations and real universe. So for instance, in terms of star formation rate, and also some of those observed protoclusters seem to have a lot more mass than theoretical, prediction, like simulations predict. So they are even, only a few selected challenges for studying protoclusters. And here is an extended list of challenges, but even this one is not complete. And in my recent work, I try to eliminate a couple of challenges of this list using some sort of simulation, some other simulations. So I've been showing one simulation named the TNG, but then here I used another simulation, new simulation named the Flamingo. And from this simulation, we found that some of those old discrepancies that have been known are resolved. So that's good news. But then new data, new simulation, new work, and new problems found. So we just resolved one older issue, which is star formation rate. But then we came up with we found another new issue that has not been known before. So, and that's about number density. So that's about like census. How many protoclusters were there when the universe was at such an age, and these are the observational data points. So a couple of months ago, with the James Webb Space Telescope, we were able to, for the first time, put the observational estimate for the how many protoclusters were there, which are these data points. But then the problem is, they are too higher than the theoretical predictions. So it turns out that this lines and the spread is sort of, prediction and the scatter in the prediction. So there are total 3,000 lines. There are total 3,000 lines, but only a few lines are consistent with the observation. So, so we've been looking into this very exciting new problem, and then we already came up with a couple of plausible explanations, but we are still further looking into this, and seemingly there are too many protoclusters in the real universe than we expected. So yeah, so I think that's sort of the no, not because of his pressure. So I will stop here. I'm just gonna leave this up, which is not real image, not even a simulation image. This is an artist impression of protocluster, which I used to show my parents when they are wondering what I'm working on. And then they say, this looks amazing. And then when I show them real ones, they just go away. So, okay, so I'm stopped here.
Thank you.